The wind causes this sign to oscillate with omega. As previously seen in our field example, we are solving problem 7.19 from the book. In this problem, you are asked to find the dimensionless pi terms of a speed limit sign which is oscillating back and forth in the wind. The given variables are omega, which is the frequency the sign oscillates, b, which is the sign width, h, which is the sign height, v, which is the wind velocity, rho, which is the air density, and k, which is an elastic constant, which was given in the problem to have dimensions of force times length. For the solution, we tediously followed Professor Troy's set of steps.
Step 1. List all independent variables that are involved in the problem.
In this step, we've taken the given variables and listed them in this form. We listed omega as a function of the 5 other variables previously mentioned. Here, lowercase k, which just signifies the number of variables, equals 6.
Step 2. Express each of those variables in terms of basic dimensions and count the total number of dimensions.
Now in this step, what you end up doing, as already here written, is you list each of the 6 variables we had previously defined, and you find the dimensions of them. You can either have the choice of doing a MTL system or a FTL system. In this example, since we were already given K as force times length, we chose FTL. So to start off with, omega is usually in units of radians per second, which is 1 over time. B, the sign width, is usually in units of meters, which is a length. H, the sign height, which is usually also in meters, is also a length. V is the velocity of the wind, is usually meters per second, which would be length over time. Now the tricky one in this problem was rho. Rho is usually kilograms per meter cubed, which would be mass over length cubed, but we are using force instead of mass. So to solve this, over here, we have shown that you have to convert the mass to a force. Now you know that newtons is kilogram meters per second squared. So if you rearrange this equation, you see that kilograms is force times squared over length, thus converting the mass to a force. So when we plug in this in for kilograms, you get force times time squared over length to the fourth. The final variable was K, which was given as F times L. And as you look through these, you count the number of dimensions. We have force, we have length, and we have time, so there are 3 dimensions.
Step 3. Determine the number of dimensionless pi groups.
To determine the number of dimensionless pi groups, which we denoted as n, you take the number of variables, subtract the number of dimensions. So 6 minus 3 is 3 dimensionless pi groups.
Step 4. For each dimension found in Step 2, assign a normalizing variable or combination of variables.
For this step, we started with length, which is usually the easiest to start with. So you look at length, you go back to Step 2. In Step 2, you see that the width equals length and the height also equals length. You can choose either of these variables and set them to length. It does not matter. For this example, we chose b equals length. So we come back to here and we see that L equals b. Also, going back to Step 2, once you have used that variable, cross it off from your list so you know it is not one of the dimensionless pi groups. So next, we come to force. So we look back at Step 2. We look which one is the easiest to rearrange for force, and we see that force equals K divided by L. And also, since we previously defined L as B, we say that force equals K over B. The final one is time. So we look again, after we crossed off K, we look at which one has time in it, and we see that velocity equals length per time. So if you rearrange this, time equals length per velocity. Again, we plugged in b for length.
Step 5 through 7. For the remaining 3 variables that were not used to define normalizing scales in Step 4, use those normalizing scales to create dimensionless pi groups.
So here, we go back to Step 2. We have already used b, v, and k. So the remaining omega, h, and rho are the 3 that are going to become our dimensionless pi groups. So we start by omega. Omega equals 1 over t. So we look here, And to get this to dimensionless, you have to multiply by t, which would therefore make it dimensionless. So omega t, and then once you have this, you take what you set t equal to in step 4, and you plug that in for t. And you end up with omega b over v. So that is your first pi group. Next, come back to step 2, and h is another one that we're making into a pi group. We see that h equals L, and we had previously defined L to be B, so to get the unit list, you divide by L, so it's h over B. That is our second pi group. Looking back at our step 2 once more, we see that rho is ft squared over L to the 4th. Coming over to step 5 to 7, again, rearrange to get it dimensionless, so you multiply by L to the 4th and then divide by ft squared, and then you plug in for ft and L what you had previously defined in step 4. So L to the 4th is b to the 4th, force is k over b, t is b over v squared. Once you simplify this equation, you get rho b cubed v squared over k. And these are our 3 pi groups.
Step 8. Express the final form as a functional relationship between these pi groups.
So step 8, basically, you take your 3 pi groups and you write them as a function. As you see in step 1, we previously defined omega as a function of the other variables, so we will stick with that here. We see that omega is omega b over v equals phi, which is the same as a function, of the other 2 pi groups, which are h over b and rho b cubed v squared over k. This is your final answer for this question, and also it was noted that omega b over v is commonly known as the Struhal number. Thank you.